All right, so we are recording. All right, so first things first, you should be writing down the essential questions. This is Chapter 8, Section 2. If you're one of the lucky few that are in my engineering class as well, you already know what torques are. We call them moments in that class. Well, no, it's a torque, because that's what all the book is going to say, is that it's a torque. Yep, torques and moments are the same thing. It's just a force times a distance. That's pretty much it. It's like anyone that's changed a tire, they know about torque. I changed a tire this morning. Yeah, it was a lovely experience. Okay, our essential questions. We have, what is torque? How is the moment of inertia related to rotational motion? And how are torque, the moment of inertia, and Newton's second law for rotational motion related? All right, and we're back. So the change in angular velocity depends on the magnitude of the force, the distance from the axis to the point where the force is exerted, and the direction of the force. For example, to open a door, you exert a force. To get the most effect from the least force, you exert the force as far from the hinges as possible, perpendicular to the door. So let's think about it. If we're looking right here, have any of y'all tried to hold the door close to the hinge and hold it open for someone? Does the door feel light or heavy? Feels very heavy, right? But then you go and you grab it by the handle that's at the very end, and it feels pretty light. Well, that's because there's something called a lever arm. So the further out, the further the lever is from where it's going to rotate, the easier it is to rotate. So again, going back to that tire I changed this morning, if I try to just turn the lug nuts using my hand, it's very difficult, right? If I tried to turn the lug nuts with a screwdriver, it would still be very difficult. So they give you a nice tire iron, which has a long L shape, and it makes it to where you have a lever arm to give yourself leverage. Okay? So force and angular velocity. For a given applied force, the change in angular velocity depends on the lever arm, which is the perpendicular distance from the axis of rotation to the point where the force is exerted. So do y'all see the lever arm here? The lever arm is the distance from the axis of rotation, so where the object's going to rotate at, to the force. If the force is perpendicular to the radius of rotation, then the lever arm is the distance of the axis. So if I apply a force and it's like this, kind of like a door, I'll end up with the lever arm being the same distance, right? That makes sense? Okay. If the force is perpendicular to the radius of rotation, the lever arm is the distance from the axis r. If a force is not exerted perpendicular to the radius, however, the lever arm is reduced. So if I see this right here, I can't always push on the outside of my wrench. It gets to a certain angle, and then I can't push on the outside anymore. I'm going to be pushing at it at an angle. So y'all see how the force here is at an angle? Y'all see that? Make sense? Okay. The lever arm L can be calculated by the equation L is equal to r sine theta, where theta is the angle between the force and the radius from the axis of rotation to the point where the force is applied. All right, so I didn't see a ton of pens moving just now, but pretty sure that y'all should have something written down. Things that you should probably have written down, you probably need to know what a lever arm is, right? You need to know that the lever arm L can be L equals r sine theta. So L equals R sine theta. Okay, so we should have had something about the lever arm. I just don't have it unfrozen for y'all. So we should have something about the lever arm. You need to have this L equals R sine theta, where theta is the angle between the force and the radius. Okay? Now, this equation right here, if the force is perpendicular, meaning that theta is 90 degrees, becomes just L times R. Sine of 90 degrees is 1, so L times R times sine of 90 degrees is just LR. Okay? So when it says that the lever arm is the perpendicular distance from the axis of rotation where the force is exerted, like this. No, there it is. Now, if the force is perpendicular to the radius of rotation, the lever arm is the distance of the axis. That's when theta is 90 degrees. Okay. Now, torque is a measure of how effectively a force causes rotation. It is represented by the Greek letter tau, which just looks like a T with a squiggle top. Squiggle top. That's tau. Okay? And it stands for torque. The magnitude of torque is the product of the force and the lever arm. So this right here. And again, if the force is perpendicular, it's just the F times the R, correct? Remember the R sine theta, this was the lever arm, and F is the force. So if I'm pushing this force on this wrench right here and it's perpendicular, the torque would be the force times this distance. Once this starts to go this way, if the force stayed in the same direction, that theta would be changing and you would be getting less torque. Because force is measured in newtons and the distance is measured in meters, torque is measured in Newton meters. Very simple. Now, a lot of y'all have probably heard the English equivalent of the torque unit, which is foot-pounds, or pound-feet if you're English, like a Brit. Yeah. 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 So it's like on your car, they don't tell you anything about Newton meters. They tell you how many foot-pounds of torque that your motor produces. But we don't really care about foot-pounds all that much because apparently no one in here is about performance vehicles. All right, so Greek letter tau, which is a line with the squiggle top T, right, is for torque. All right, so it says, what force is applied when the wrench from example problem 1 is used with a 35 Newton meter torque applied at an angle 75 degrees from the perpendicular? So this means I need to look at example problem 1 in the book to do this. So this is what they gave us in the book. It's not supposed to be giving me my answer way up there at the top, though. Oh goodness. Come back. Okay. So sketch the situation, list the knowns and unknowns. So the situation is that I have this wrench, and it is turning this nut. So it goes around, and we'll be good to go. So they said that the torque is 35 Newton meters, and they gave us that theta is 75 degrees. The R is 25 centimeters. The unknown is the force. So what do we see as a problem at this point? we should see some problem. Look at our knowns. There's a problem. No, there's a problem inside our knowns, our givens. Can anyone spot it? Different units. That's right. The tau was given in newtons times meters, and the R was given in centimeters. But we can convert that pretty quickly. So if I have 25 cents and I wrote it as dollars, it would look like R is equal to 0.25, right? Same thing for meters. Yeah. So this is 25 cents. This is 25 cents of a meter, right? Okay. All right, so our unknown is the force. What equation can we use? That's right. Tau equals F times R sine theta. Okay. So this should be pretty straightforward to solve, right? We got 35 equals the force, which is our unknown, times R, which was 0.25, times sine of 75 degrees. So you throw that in your calculator, which I'm going to go ahead and wait for everyone to get their calculators now. I saw a big problem on the last test where people didn't know how to use the trig button on their calculator. So I'll wait. All right, now that most people have calculators, I'm going to go ahead and solve this for F. That means I just have to divide by 0.25 sine 75. So on the calculator, the way we do that is we do 35, divide by, and we're going to use a parenthesis because we want everything at the bottom to be stuck together. So that'll be 0.25 trig sine 75. Hit enter. You get that tau is equal to 144.9. But we only have 2 sig figs, so that rounds it to 140. I'm sorry, F is going to be equal to 140 newtons, not tau, because we solved for F. So the force was multiplying times 0.25 and multiplying times sine 75. So I divided by 0.25 and sine 75 on both sides of the equation. So 35 divided by the 0.25 sine 75 gave me 140 newtons. Okay? This is the common mistake I'll see in the calculator. Someone will do 35 divided by 0.25 trig sine 75. It looks not too bad, right? But you got to remember, your calculator is dumb. It's going to do exactly what you tell it to do despite what your intentions are. Okay? So it's really good at looking things up, but it's not very bright. So to you, when you put that in, it looked like you did 35 and you told it to divide by 0.25 sine 75. That's what you told it to look like, right? But the way your calculator interpreted this was you did 35, you did divide by 0.25, and then you did multiply by sine 75. So instead of the 0.25 and the sine 75 multiplying times each other, you did this operation, then you did this operation, then you did this one. So really it put the sine 75 at the top instead of at the bottom. Okay? So make sure if you're going to divide by multiple things, just throw it in a parenthesis. Or if you're really crazy, use the magic fraction button. Because the magic fraction button lets you do it correctly every time. So if I had, for instance, started by using the magic fraction button, I could have put 35 on top. And then on the bottom, I could have put 25 sine 75, and I would have got the right answer. Well, yeah, I was supposed to do 0.25. So you can still mess up even if you know what you're doing, apparently. Okay? All right. Concepts in motion. We're going to see how good a video goes on the video. I don't know how well it's going to work.
Get 2 pencils, some coins, and some transparent tape. Tape 2 identical coins to the ends of the pencil and balance it on the second pencil, as shown here. Each coin exerts a torque that is equal to its weight times the distance from the balance point to the center of the coin. The torques are equal and opposite in direction. Thus, the net torque is 0. You could add a second coin on top of one of the 2 coins, thereby making the 2 forces different. This makes the net torque greater than 0. Hence, the pencil rotates in the direction of the net torque. You could also slide the balance point toward one end or the other of the pencil, thereby making the 2 distances different. The pencil again rotates, but this time due to the difference in R1 and R2.
Okay, so basically if we have an object, and that object has the ability to rotate, it will, unless all the forces times the distances balance out. So whenever the forces times the distances balance out so that the object's not moving, we call it in either equilibrium, or we'll say it's in static equilibrium. Which again, if you're in one of my engineering classes, you know what static equilibrium is. It means it's not moving. My engineering student in the back now remembers. Okay. Oh my goodness, they're all about using the example problems from the book today. It says, suppose that Aisha is replaced by a 52-kilogram Mario in example problem 2. Where should Mario sit? Well, we have to kind of see whatever was in the book. So this is the setup. It's basically like your classic teeter-totter scenario. So you've got one person sitting on one side of the teeter-totter. You have a place where it can rotate in the middle, and then you have another person on the other side. Are y'all familiar with the teeter-totter? Also known as the Toddler Launcher, right? It's like when the big Uncle Jeremy takes the tiny nephew or niece out, and they hit on or sit on one side, and then I sit on the other side, and they go flying in the air, and sometimes they cry. That's the teeter-totter. Okay? So, what they're saying is Mario's mass is 52 kilograms. Whoever K is, their mass is 56 kilograms. The force of gravity for K is 550 newtons. That's just 9.8 times the 56. The length is 1.75, so I'm guessing that's the total length is 1.75. And they said RK is 0.76. Okay? So, I'm going to come up and I'm going to label everything on the free body diagram because that's going to make it easier. Said RK is 0.76. You're probably going to want to draw this into your notebook. L is 1.75. So the length from here to here. So the length here is equal to 1.75. It says RK is 0.76. Got that. MK is 56. MM is 52. They said the mass of Mario is 52. And so to get the FG for Mario, it'll be 52 times 9.8. Okay. So what we're trying to do is balance this so that whoever K is, I don't know who K is, but whoever K is, we don't want them going flying up into the air. We want this to balance out so that they're not flying in the air, right? So, like, for instance, if I take my niece and nephew and I sit them way at the end of the teeter-totter and I'm kind of here close to the balance point, we can balance together, right? Yeah. If I set one of them at the very close and then I'm at the very, very end, they go flying really bad. Okay? So, we got to figure out what the R for Mario should be. Okay? So what we're going to do is we are going to set it up so that the sum, remember sigma, looks like that weird looking E thing, of the torques is equal to 0. Because we said we wanted them to balance. We want them to be in equilibrium. So the sum of the torques have to be 0. Okay? So we know tau K is going to be equal to FGK times RK. Right? That's tau equals force times the distance. Notice that it's perpendicular, so I didn't have to put the sine theta. Okay? So tau K is FGK times RK. Tau for Mario is going to be FG for Mario times the radius for Mario. Okay? Now let's look at this. If I look at the point where I'm seeing this rotation, look at this point. Is this going to make this bar bend around counterclockwise, or is it going to make it go clockwise? Look at this force. It'll make it go counterclockwise. And counterclockwise is positive. So this one's going to be a positive torque. I'll write it down here. So that one's going to be positive. Now I look at this one right here. So again, this is my center point. So everything's going to rotate around here. Is this force going to make it go clockwise or counterclockwise? Clockwise. That means that Mario's tau is going to be negative. All right. What's up? The 0.76 was given. It was for, That's why I wrote it down. It's 0.76 meters. Okay, so I'm going to plug in the equation now. So I'm adding up the taus, right? So that's going to be tau K plus tau M, right? Okay, and tau K was FGK, which was 550, and it was positive, right? Times 0.76. Tau M is going to be negative, right? And it was 52 times 9.8 times RM. And all this has to equal what? 0. Okay. Now I'm going to erase all this because I'm running out of room. All right, so I'm going to add this 52 times 9.8 RM to both sides. So that's plus 52 times 9.8 RM to both sides. So now I've got 52 times 9.8 RM is equal to 550 times 0.76. What are the 52 and the 9.8 doing to RM? They're both doing what? They're both multiplying. And the opposite of multiplying is to divide. All right, so this is when you take out your calculator again. So you can use the magic fraction button. Come on, magic fraction button up here. There it goes. 550 times 0.76 on the top. On the bottom, I got 52 times 9.8. And what do I get for my answer? 0.82. So I get that R for Mario is equal to 0.82 meters. I've got a question now. Will this work? I don't know. Will it or will it not? Why wouldn't it work? Well, Mario needs to be at 0.82 meters to balance. So way back, one of the givens down here was that the total length of the beam is 1.75 meters. So I got to check real quick just to make sure that it'll still work. So 0.82 plus 0.76, that's going to be 8. 7 plus 8 is 5. 1.58. Is that less than the length of the beam? Oh, man. It still balances. Good. So, for instance, if this had been like 1.2 and 0.76 was the other side, they wouldn't still be on the beam, would they? So it wouldn't have worked. Okay? So, those are just some things to think about, and you can check. All right. Moment of inertia. Now, this is the part that we're not going to cover as much other than to just talk about it. We're not going to really get into it and dive deep. Okay? The resistance to rotation is called the moment of inertia. Nope. This is just all going to be the knowledge part. So I told you that the torques was kind of important. Moment of inertia explains some stuff that you already know. So for a point object located at a distance r, the axis of rotation, the moment of inertia is given by the following equation, I equals mr squared. Okay. Newton's second law for rotational motion states that the angular acceleration is directly proportional to the net torque and inversely proportional to the moment of inertia. So you can see here that there's something involving the angular acceleration and the net torque and the moment of inertia. But it's not one of those things that, like I said, we're going to be calculating in this class. It's not as important. But basically, torque and angular velocity, they work together, is all it's trying to tell you. Yep, so that's it. All right, so again, I'm not picking up the homework that was due today because my afternoon classes don't get that same opportunity to be late without me counting a penalty. So for my first and fourth period, I'm not picking it up. However, on Tuesday, I will be here and I will be taking the homework from last week, so make sure you get it done.